Okay, we started recording. Okay, so hi everyone. I will just want to touch on something that was on a set of slides last time. I didn't get to it. It's kind of important because it like sort of shows you how to model building blocks and how to put them together. So what's the right notion of a key exchange security-wise? We never really defined it. We just said, well, we defined it in a kind of informal way. As well, actually, we didn't define it. We just said it's hard to compute a key, and we saw attacks, and we saw like man-in-the-middle attacks, which was argued that the computation of the key is as hard as is hard by the Diffie-Hellman assumption for the Diffie-Hellman key exchange. Okay, let's see what the right notion should be. So, okay, so here is again a Diffie-Hellman key agreement, and Diffie-Hellman assumption says that computing these keys, that if you watch, so security is still against just honest but curious, passive, eavesdropper adversary. He gets this transcript, and Diffie-Hellman assumption says that if you get a random transcript here, random two elements like this, computing this function is infeasible for a polynomial time attacker, except for negligible probability. So, okay, but is it enough to ask that it's hard to compute the key? What if it was hard to compute the key in its entirety, but half of the bits of the key were leaked? It would still, because half means that even if you get half the bits, guessing the rest is infeasible because half of the polynomial is still polynomial, and but you clearly wouldn't want the key exchange to be like this, right? Because if you create a key and say, okay, it should be that it's like a perfectly random key. So let's say the key has 200 bits. You first take 100 bits to secure traffic from Alice to Bob. The second 100 bits for Bob to Alice. If left side of the bits leaks, then there's no security for Alice in this scenario, right? Or what if half of the bits were used for macking and half of encryption? So you're gonna lose one of these two properties because of that half which leaked. So what we want is that it's not just hard to compute, it's hard to distinguish a key from random. What does that mean exactly? It means that even if somebody gave you the key afterwards, you cannot correlate it with the transcript. If you were an outsider, right, like just an eavesdropper, this is similar as in security of encryption. Even if I tell you what's encrypted, you cannot verify it. You cannot correlate it with the ciphertext. That's the indistinguishability of encryption. Even if you had a choice between just two messages, M0 and M1, you knew for sure that one of them is encrypted. You still, even given that information, you cannot decide which of the two is more likely. Okay, so it's like this. So, but for key exchange. So, how do we model this? That it's a pseudo-random output of a key exchange. Well, sort of similarly to how do we model pseudo-randomness of a PRG? We say, okay, an PRG output is pseudo-random. In what sense? For any efficient attacker, if you give him output of a PRG versus you give him a completely random string, attacker cannot tell a difference. Likewise here, what we're going to say is like, if you give him the right key and a transcript of a key exchange, versus you give him a transcript of the key exchange, but followed by a completely random key, he cannot tell the difference between these two views. In that sense, the output of a key exchange is indistinguishable from a random string to him. So he's given the transcript, and in one experiment, he's given the right key. In the second experiment, though, this is like a real key exchange game, right? Like a key exchange executes, attacker gets the transcript, and then the good guys, so key exchange executes, right? Attacker sees it. That's a transcript. Then the two good guys, Alice and Bob, they output the key. Attacker also sees that. Attacker sees everything. Okay, but in this ideal key exchange game, you compare this to what happens is that you give him the transcript the same way, but then you follow it by a completely independent key. And he cannot tell the difference between the two. So how is this different from a PRG? There is no notion of a transcript, right? Like a PRG just gives either output of a PRG on a secret seed or a completely random value. But it is important here that the adversary observes this. He's an eavesdropper, so he gets a transcript in either experiment. It's just that he cannot correlate the real key from a random one. If this is like a PRG, then where is the seed? There is some, this is a challenger who runs a cryptographic experiment. Adversary has a certain view of it. There might be some secret underlying here that allows this view and this view to be indistinguishable. That secret is the randomness of Alice and Bob. So because there is no inputs, right? There's no key that they share. There is no random seed. But in a sense, the role of a random seed is played by the randomness of Alice and Bob. If you remember, Diffie-Hellman's is the little exponent A, little exponent B. They both function as trapdoors. The good guys pick the little a and b, give the view based on that, g to the a and g to the b in the case of Diffie-Hellman. If adversary saw the trapdoors, the secrets behind the public view, which is like seeds behind a PRG string, then he would immediately link it, right? Because it's that given the randomness, computation of everything is deterministic. So in the case of a Diffie-Hellman, if adversary breaks the discrete log and he finds these little exponents, then he could recompute this. And in particular, this part, and therefore, whereas the same recomputation will fail in this case, right? So that he distinguishes. So that's the hook on which security of this can work. Yes, sorry. So the key, somebody says this is my notation for an output of the key exchange. So this is the key exchange output on the Bob side and the Alice side. They might have been called KB and KA on some previous slides. And because it is just security against eavesdropper, I don't consider adversary interacting here. So in particular, these two guys are guaranteed to output the same key. Yes, because if nobody interferes, then by protocol correctness, these two keys, the output are the same. So this is well defined. If we upgrade the notion to active attacks, then basically there will be a separate key for Bob and a separate key for Alice, possibly, because adversary here is man in the middle. And we would, if it's secure against active attacks, then both of these two keys given here should be indistinguishable from two random. Okay. So it gets a little more hairy. in that case. Okay, so security is the inability is that for any polynomial time attacker, this view and this view are indistinguishable. In other words, the real key exchange and in some way idealized key exchange, cheated key exchange, where the real transcript is followed by a independent key, are indistinguishable. Why is that a useful notion? Let's first see that. So that's the simpler. Okay. So okay. Okay. So as usual, formally we just say probability in this case of outputting anything, and in this case outputting anything should be negligibly close. Okay. So, oh, sorry, this slide is badly badly titled. I have to just quickly change it. Okay. Hold on. Okay, I'm back. Okay, it was a bad title because this was not a Diffie-Hellman key exchange. Remember, we said that one thing that the public key encryption immediately gives you is a key exchange. So Alice forms a public key, sends it to Bob. Bob chooses a session key X, and he sends an encryption of the session key under her public key. So there is no security. It's only for eavesdropper, right? Because the active attacker can replace it by his own key, and this whole thing is passed. But if there is only eavesdropper, then what does adversary see? Public key and an encryption of the session key. And now, by indistinguishability of this public key encryption, and CPA is so it's indistinguishability under the CPA attack, which I was arguing is this equivalent to just indistinguishability for the public key encryption. Adversary cannot distinguish a pair that looks like this, public key and an encryption under of a session key, from a public key and encryption of an O0 string. This is arbitrary. You can put any constant here or an independent random value, right? If an attacker saw a difference, reacted differently to this view and this view, then you will have an attack on indistinguishability of encryption E, right? The reduction is going to pick one message as X, the other is this, and if the attacker, and just forward ciphertext to the attacker, if he sees the difference, then the reduction is going to see the difference between encryption of left message and encryption of right message. And the only thing the reduction has is the public key. So that's an attack on indistinguishability of this encryption E. And this basically, so it's vulnerable to attacks in the middle. But if you have this notion, then this will satisfy the notion I have here, right? Because what will be here? It will be public key and a ciphertext. Okay. So how do I argue that the public key and a ciphertext and a real key is then indistinguishable from public key and ciphertext and some random value? Hold on. This. Okay, so in one game I see what the attacker gets is a transcript, which is a public key and a ciphertext encryption under the public key of key K, and he gets the key K. So let's call it key K, and he gets the key K, and key K is taken at random, like this. Let's say 128-bit string. The focus better. Okay. Okay. And I want to argue. So this is the game 0. This is what happens in reality when you interact with a key exchange. So you're not getting, in reality, you're not getting a key. In reality, you will get some function of the key because people are going to take this key and use it. That's what we're going to argue later. That this is, if you can show that given the key, you cannot distinguish from random, then it will follow that people can use this key securely for anything they want. Okay, so that's the second part. Let's now see that this PKE-based key exchange is secure if the encryption is insecure. Okay, so my target game G1 is, I want to show that this is indistinguishable from the following. You got a public key and a cipher, but you follow it by a completely random, independently random key K. So here you pick key K again from the space, but you pick the key star again at random from the same space, independently from this. So this is a random choice, random choice, random choice. Okay. Now, by indistinguishability of encryption, let's consider geo prime modified real view. That would look like this. Transcript is a public key. Ciphertext is an encryption. Okay, well, let's write this of 0 concatenated. So this is an all 0 string, right? And then adversary gets that, and then gets the key. And as before, key is chosen at random. Now, so first thing to note, if E is indistinguishable, then G0 is indistinguishable from G0 prime, right? So that was the reduction I was hand waving in last slide. The only difference here is this ciphertext Z0 encryption of K, or ciphertext encryption of an all 0. If A saw a difference here and here, then a reduction would pick this key, ask the encryption oracle to encrypt either this key K or an all 0 string, and then embed the ciphertext into the transcript, right? And that reduction would, if this guy behaves any different, then the reduction would succeed in breaking the distinguishability of encryption. Okay, so we are here now. Note I can now do this. That doesn't change anything, right? It's just up to a name of the variable. Okay, so what's the difference here and here? I guess another instance of indistinguishability. So fact 1 was this, and fact 2, if E is indistinguishable, then G0 prime is indistinguishable from G1. What is the difference between G0 prime and G1 prime? in both cases, some key is chosen and given to attacker here. And independently from that, in first case, in G1 case, so PK is chosen, using the standard key generation algorithm in both cases. And this ciphertext encrypt an independent random key, while this ciphertext encrypt an all-zero string. So again, you have a reduction, right, which given the encryption challenger for indistinguishability, right, gives him a public key. Reduction sends, and the reduction chooses K at random and sends two messages, M0 the key, M1 an all-zero string. This guy sends a ciphertext, which is an encryption of MB for this random bit B that the challenger has. And this guy just forwards now a public key and a ciphertext. And moreover, also independently, okay, so let's move this arrow here. It chooses just K star at random and sends this K star as well. The attacker sends some bit. The reduction just forwards the same bit. Yes, and so because this key is independent, the reduction can still succeed, right? And now by these, we get that G0 and G1 are indistinguishable, right? And this is what we wanted. Okay, so this is why this is true, right? That indistinguishability of encryption implies any questions on this stuff. Okay, so this argues security of the simple key exchange that satisfies this notion. What about key exchange, Diffie-Hellman key exchange? So this is a little harder because, I mean, okay, this is not harder, but formally, I mean, syntactically, a key that's created by the Diffie-Hellman key exchange is not a random string. So this would mean that in a real Diffie-Hellman key exchange, this thing is a group element, right? It's G to the AB, mod some prime. Or in the case of elliptic curves, there's some elliptic curve element that satisfies elliptic curve equation. This here is a random bit string. So anyone can differentiate between a random, a group element that has structure and a random bit string that does not, right? So encoding elements of of groups as random bit strings, it's possible for some groups and somewhat hard for others. So they could use some, if there was an encoding like this of group elements as strings in such a way that a random group element would be encoded as a random bit string, that would have many applications in crypto. If, like I was talking to this, I suppose, undergraduate class, it was on, for example, covertness of cryptographic algorithms. So you want to have like a Diffie-Hellman key exchange that nobody can distinguish between that and random bit strings. So it's undetectable, can be embedded in random strings. So if there is any random noise on the internet, then it can be embedded into that. But Diffie-Hellman key exchange messages are group elements, right? So elliptic curve elements. So that would be one application of this. And then here will be another. That's why what we do in so this is so-called textbook Diffie-Hellman, where the key is a group element. In the real Diffie-Hellman that we use in practice, we don't use the group element itself as the key, we hash it. Technically, this can be called a hashed Diffie-Hellman key exchange. So the only difference is that you take this final key and you hash it. Now, a hash of a group element, let's say you use SHA-256, this key therefore is a 256-bit string, and now you have a chance for this security notion, right? Because now this is a hash of a group element, and this is a 256-bit strings, and now at least syntactically they look like the same type of objects, but it's more than syntactic. So here, the question is, what do you need to assume about this hash? How strong should this hash be? If you know that this input to the hash has a lot of structure, like for example, satisfies elliptic curve equation. On the other hand, it has, let's say that it had a real entropy, meaning it was a random elliptic curve point. It is not a random elliptic curve point given this stuff. It's actually deterministic given the transcript. But that's the difficulty, because it's not a real entropy. It's something called pseudo entropy, like pseudo randomness. If this input had real entropy, what kind of hash would you need to translate the entropy here into entropy over the outputs of the hash? So let's say that the hash was, in a sense, perfect. Like, let's say that there's 2 to the 256 elements here. And these are 256-bit strings, so therefore the domain and the range have the same number of elements. If the hash had no collisions at all between this domain and this range, then clearly a random choice here, this is some one-to-one function, gives you random outputs here. But hashes have collisions. It's just that they are collision resistant. That's what they're designed for. So that simple argument based on the one-to-one property of this hash function, right, does not quite work. So what kind of hash do you need? Okay, and if this was like any collision-resistant hash, SHA, do I have a guarantee that if my inputs are not random but pseudo-random, indistinguishable from random in some domain with sufficient entropy, like an elliptic curve with 2 to the 256 points, then is the distribution of the outputs of this hash, do they look like random 256 bits? Or they possibly could have some correlations that are detectable through an efficient algorithm. Here is a lemma by Michael Luby about a 2 universal hash. So 2 universal hash is that thing that we used in Carter-Wegman one-time math construction. You were supposed to read up, so like I didn't go over this part of the slides in my talk, but you were supposed to read that part. The way it worked is that the key was a random AB pair in the modulo some prime, and the hash divided the inputs into blocks that fit into this domain mod P, and computed the polynomial whose coefficient whose on the input the key a, the a part of the key. So you take a square, a cube, a to the fourth, that's the polynomial, and the coefficients in the polynomial evaluation are the blocks of the input. So in this case, you would take this elliptic curve point, you would encode it in binary in any way. It is encoded in the binary. Okay, so not as it wouldn't be a random string because it has verification procedure, right? Which a random string does not. And it would use chunks of this message encoding as input to this polynomial evaluation. Okay, so that's a two-universal hash. What does two-universal mean again? It means that in an experiment where adversary chooses, okay, so it's actually information theoretic. So in a two-universal hash has this following property. On any two messages inputs in the argument space, x1, x2, the probability that the hash, this hash h hashes them to the same string, where the probability goes over the choice of the key, hash key, is the probability is 1 over the size of the space. Now, that's true about this polynomial evaluation, so it gives you a two-universal hash. And also that suffices to translate not only entropy, but also pseudo entropy, so pseudo randomness of the inputs, to pseudo randomness of the outputs. So the outputs are going to look like independent random strings. You lose entropy in this transformation if what Luby shows is that if this input has say n bits of entropy, the outputs have n minus twice security parameter. So that loses quite a bit. However, this doesn't mean that there is an explicit attack that does any better. It just is the best that this two-universal hash could probably do. Two-universal hash has a key. Where is the key here? Well, it could be part of the description of the hash function. So actually, it's a public value. As long as it's randomly chosen at the beginning, it can be reused. Why? Because the input is not chosen adversarially. It's a pseudo-random input. So normally, in a universal hash function is insecure in the following setting. I've announced what the key is, and now adversary can pick messages that hash to the same thing. The low probability of finding messages that hash to the same thing is if you first fix the messages and then I choose the hashing key, not the other way around. So this is a very highly non-trivial result. That any hash function with this universality, which really worked under a different setting for different purposes, can be reused and can be actually a public function, which can be applied as the kind of public extractor of randomness. I feed it this complicated high, source that the elliptic curve points, which have a lot of structure. Whatever the structure is, this compiler does not care. the moment this thing has some entropy over its group, the outputs have entropy or pseudo entropy, right? So they're indistinguishable from strings which have n bits of, there are pseudo random. Okay, so they're indistinguishable from a random string. So we have, I believe we already introduced this notion of a random oracle hash. So in practice, you could put a stronger thing than a 2 universal hash. You could put SHA, which not only, I mean, it's stronger or weaker, it's just different sort of apples and oranges. But even given the function description, meaning all keys about it, if there existed, they are published here as a description of the hash. And no polynomial time attacker can find 2 inputs which hashes to the same, right? So in that sense, it's stronger than a 2 universal hash. And in a mode of, there is a way of analyzing protocols where instantiable the hash function. It's called analyzing it in this called random oracle model for a hash. The random oracle model is like, okay, well, we should sort of introduce this more slowly. But the basic thing is like as if this hash is a true random function. It's a true random function in the sky. So everybody can access it, because indeed everybody can compute SHA-256. But if you just have an input-output relation access to this hash function, then the outputs that you get on any inputs, they look to you like random string. And the only way there is something non-random about it is that if you happen to ask this hash function to compute on the same input twice, then it, of course, outputs the same value twice. You can see that the random function here would be like a perfect compiler. Does not matter how much structure these inputs have. On any different input, this random hash function guarantees that it will just output random strings uncorrelated with anything, as long as it's queried on different inputs. So you don't, this whole result you just get for free if you assume that SHA is like a random function. And in practice, in many cryptographic applications, a lot of stuff that runs in practice, this is an assumption that is taken. It's nice to be able to avoid it, like for example, using Birokov, but it has it's imperfect anyway. As I was saying, it loses entropy. Okay. So now, okay. Let's see why. Oh, sorry. Let's see why. Okay. One thing that this so hold on. Let's say I have a Diffie-Hellman key agreement where both of these parties compute G to the AB, but then they hash it. So that's the key. And the same computed by the other side, right? So what the adversary gets is the transcript, which is the two Diffie-Hellman key exchange values and the key hash of GAB. So that's game 0. The game we want to show that is indistinguishable from this, followed by a random PK, right? So in other words, the transcript here is G to the A, G to the B, and it's K star chosen at random. Okay, so in this case, hash takes anything into 128-bit string. Okay. So what? So here is security theorem number 1. Assuming that Diffie-Hellman function is hard to compute, which is called, this is called computational Diffie-Hellman assumption. And H is a random oracle, i.e. a random function. Then hashed Diffie-Hellman key exchange is secure. Okay, so this view and this view are indistinguishable. And the proof sketch is like this. So consider case 1. So you have an attacker. He's given this transcript, GAGB, and he's given this key. And the attacker can access a hash function. On any inputs, it gives him, but this is a random random function. And given this type of interactions, the attacker outputs a bit, right? Okay, so this, okay, let's not designate it because I don't want the bit to look like this little b. Let's consider 2 cases of attacker. Case 1. So he sends some inputs to this hash function and gets values. YYI is hash of xi. Case 1. There exists an I such that xi is equal to g to the ab. In other words, a hashes g to the ab. And if you know, the formal stuff would be that this happens with the high probability, with non-negligible probability. And it's immediate, basically, that this such a will break the computational Diffie-Hellman assumption. Yes, because I'm giving him G to the A, G to the B. He does whatever, and I just output random values because I'm random function. And here, by the way, what do I give him here? Well, in fact, the reduction sets K to be random. Because if H is a random function, then you cannot tell anything about this value, which is an output of the random function, before you query the input, right? Because outputs of the random function are just random values unless you query the pre-image of this function H to this box. Then this box will tell you what the value is, and then, for example, you can check whether this is the same or not. But that happens after you query the input. So if you are the kind of algorithm, whoever this appears, you will, if this is real or this is random, you cannot tell, and I'm up to this moment. So therefore, the probability that this event occurs, even though the attacker, rather than getting the real hash of G to the A, B, gets a random value, the probability does not change if H is a random function. Okay, so that's the kind of a key thing that allows this argument. And so therefore reduction can set this value at random and just guess index I such that xi is G to the AB, because the reduction cannot verify. The reduction gets G to the A, G to the B, and even if some of this is correct, reduction wouldn't know, right? Because it's, so what? You cannot correlate. You're getting a G to the AB. How can you tell this unless you know the little exponents? But it doesn't matter because you know, with 1 over polynomial probability, reduction is correct. So if this guy has an probability, you know, certain non-negligible probability of distinguishing, of getting to this event, then with probability 1 that over some polynomial, which is however many things are being queried here, the reduction will output the correction to the AB and therefore break the Diffie-Hellman assumption. Okay, and case 2 is an even simpler one. You know, A never hashes.
Professor? When you are replacing K by random, you are already using the Diffie-Hellman assumption, right? Because
no,
otherwise,
because
when you replace, after you replace, you could ask for the random function age at GAB.
Right.
And then you would test it again.
Yes, but you do this after this event occurs. Right? So all I'm arguing here is that if I replace K with a random, I'm not changing the probability of this event. So let's say that in this interaction, when adversary gets the transcript and the hash, this event has some probability. Let's call it epsilon. Now let's modify the view so that K is no longer real. It's not hash of the real stuff, but a random. This event still occurs with probability epsilon. Because the only way to distinguish a random value from the real hash is after you make this query. So the probability of making that query does not change, and that's the only thing you care about. Because after this query is made, then okay. So that's why. And if it never hashes G to the AB, then basically we get indistinguishability of this and that already. Okay, so first, we have to discount this event, which can be discounted by the computational Diffie-Hellman assumption. And then once this event is not happening, it's bounded by a negligible probability, then except for that negligible probability, adversary doesn't hash. And that means that we can straight away replace this key with the random, and adversary view doesn't change because xi never equals to this right value now. You can avoid this random oracle model if you instead, so it's the same protocol, but now you say, so security theorem number 2, if H is universal hash and so-called decisional Diffie-Hellman assumption holds, then the hashed DH key exchange is secure. Okay, and now what is decisional Diffie-Hellman assumption? The assumption is like this, that if I give to an attacker input, a tuple like looking like this, where A, B are random in the order of the group, let's call it Q, and I give this to an attacker, or I choose an independent random group element instead of G to the AB, and give it to the attacker, then he cannot tell the difference between these two. Okay, so if he makes some judgment, he cannot tell the difference between these. This is equal to the decisional DH assumption means that any efficient A cannot distinguish these two views. Okay. So the proof then would work a little differently if you, given this view, if you cannot tell it from this view, then I can replace it to the AB with a random G to R, and you cannot tell, and I will have a reduction like this, and then by a universal hash of the G to R, because R is independently chosen from the group. So this is a group element that is independent from these two. So I can use the universal hash and argue that the output of a hash on this independently chosen group element is indistinguishable from a random string, and therefore I got here. If you compare these two theorem statements, they're sort of like apples and oranges. This one uses computational Diffie-Hellman assumption, which means that if you get this part, computing this is hard. Decisional, this one uses a stronger computational assumption. It says, even if you got this part, you cannot verify it in the following strong way, that if you got instead a random independent group element, you couldn't tell a difference. indeed, for most groups, we don't know how to tell these exponents from exponentiations from just independent group elements. For some, however, some elliptic curves have what's called a bilinear map, which precisely gives you a trapdoor that allows distinguishing these two. So these distinguishing these two bilinear map allows, but it doesn't allow to break the computational assumption. If you were given the answer, then you could verify it. But given the G to the A, G to the B, we still don't know how to compute this answer, even in those groups. So computational and decisional Diffie-Hellman are distinct. There are groups where this problem is easy and this still remains hard. So this assumption doesn't come for free and is indeed stronger. But here I used a very strong assumption about the hash. And here I could, replace it by a much weaker one. Okay. So both of these basically explain why this is done, and they explain it in a sort of, in two different ways. Okay. So we got that for the Diffie-Hellman. We see that why this security notion is achievable. And we saw this for the encrypted public key exchange. So finally, why do we have this notion? Okay, why is this a useful notion? Why is it okay to say that why key exchange security is framed as indistinguishability between key exchange happens and creates a transcript, and also the key versus the key exchange happens, creates a transcript, but then there's an independent key chosen at random, and the real key is replaced by this random one. And these things are reached, they're given to the adversary, and we say this game 0, game 1, as the G0 is indistinguishable from G1 for any efficient A. Okay, so why is this a useful way to state things? Right, so this is the question mark. So we would like, years ago, we would like the following to happen. We would like that if A and B are engaged in key exchange, and then they output some key because of this, and the transcript of the key exchange is observed by, so this is Alice, so this is adversary, right? And this is Alice and Bob. So adversary gets the transcript, and so far he doesn't get information about the keys, but the keys are now used for encryption and authentication, right? Or some other, basically they are fed into any symmetric crypto. We would like to say that this is as if A and B did something irrelevant, which adversary received, and I'm going to call the irrelevant thing a key exchange. And then, independently of this, a random key just was chosen and given to these people, Alice and Bob. And these people fed it to the same any symmetric crypto system, right? So think of this as authenticated encryption, right? Like or authentication, encryption. Maybe they expand it using PRG. Maybe they use it for a PRF. No matter what they do, sorry, this is K-star. Now, let's look first on the left-hand side. An adversary engages in this symmetric crypto system by the ways that are allowed in this crypto system. So, like if this CC security, CC secure encryption, right? So this means adversary can choose messages and sees what they encrypt to. If this is maxed, then he chooses the messages that are going to be marked, etc. He engages. This is any symmetric crypto game. Then let's look at the right-hand side first. The right-hand side is an ideal key exchange. Something happened, adversary gets the view of that. And then, by magic, a key was created that has really nothing to do with this part, right? Because it's independently random choice. And then this K-star is what was used in asymmetric crypto systems. So now, if we're using secure crypto systems here, then we already know that if the K-star is chosen at random, as we assumed throughout the first part of this class, then these crypto systems achieve security. So whatever their functionality was, like for example, authentication and encryption, efficient adversary could not interact with this thing in a way that broke it. So we have security here is secure by first part of the class. Okay, and now I want the same security to hold, even though this magic choice of the key of the random key on two sides of the network for Alice and Bob does not happen in reality, right? In reality, the key is chosen by the key exchanges and an output. So, but I want everything I learned and I could do with symmetric cryptography to carry over and be just as secure. So if here adversary got sort of nothing useful by this, whatever that meant, in the context of these crypto systems, I want the same to be true here. And this notion will give it to me. Because if key exchange is the case that transcript followed by key is indistinguishable from transcript followed by random, then this is exactly what is allowed to replace this game. So if adversary here, just conjoined adversary, first of all, he saw transcript of key exchange, then he worked against these crypto systems. Now in this idealized world, he gets a transcript and he works against these crypto systems. In the idealized world, it's clear that this transcript is irrelevant, right? It's some protocol that outputs some stuff, but it has nothing to do with the rest. So how can this information help? It cannot. Okay. Now, if the event of breaking crypto systems is well defined, as it always is, and in this world, the probability of this event was epsilon and it was non-negligible, then it would have to be epsilon minus negligible here. Or otherwise, you have a reduction that distinguishes G0 from G1. What does so this is the real and ideal. Let epsilon the probability adversary breaks symmetric crypto game in the real world. Let epsilon prime be the probability that adversary breaks the symmetric crypto game in ideal world. If now fact one, epsilon prime is negligible. Okay, so by security of symmetric crypto. And two, epsilon, the real epsilon is negligibly close to epsilon prime by security of the key exchange. Okay, and here, so two follows if adversary distinguishes real and ideal, and therefore makes this event of breakage in here different, non-negligibly different than the event of breakage of the symmetric crypto here, then there is an efficient reduction which distinguishes G0 from G1. How would this reduction work? It gets a transcript and a key. And then the reduction uses this key for symmetric crypto, emulates all these processes, gives the transcript to the adversary straight away, and uses the key to emulate this. And it's obvious that this reduction distinguishes G0 and G1 because the transcript is the same. So the transcript is the same, but the transcript is the same in these two. If the key is formed as in G0, then this reduction emulates the real picture because it took the real key and plugged it into whatever symmetric crypto system world. If the key was an independent K star, then the reduction emulates this picture, right? It had an independent K star and it ran symmetric crypto on it. So this reduction distinguishes between these two if there is an attacker that can distinguish this from that. Okay, so this really shows you why this is a robust notion. Everything that you knew about symmetric crypto, you can now reuse because key exchange accomplishes like this transmission, this shift. Basically, it means that the key exchange was irrelevant. The key is as if chosen by magic, randomly on both sides of the network. So for next time we'll look in we need to get a little bit take a few steps down and look at some basically attack on discrete logarithm, see why these systems how do you get a fast so let's look at a little bit of sort of modular arithmetics and see why exponentiation is fast. and why discrete logarithm, you know, seems hard, and therefore all these assumptions, computational Diffie-Hellman or decisional Diffie-Hellman, can you know, can be believable, and yes, and also like just learning a little about modular arithmetics would allow us to look at RSA case, right? So El Gamal is one public key encryption, but you should also see the RSA case. Okay. If you do you have any questions on this stuff? Well, yeah, okay. Sometimes I get the feeling that that I'm, you know, that this stuff is like basically more theoretical. I mean, maybe you're getting some things, like, or at least some of you, that that this, you know, that these notions make sense, and that you can combine them, and that they, you know, how would the security arguments look like, and etc., etc. But it's, I think it's hard to engage, because it's like a theory where, like, you know, what more can I do with it? Or like, so okay, so this is true, but like, what can I build on top? Or like, how I make minimal changes and something completely collapses. And all of these things are kind of true. Yes. But that's still a good thing to see, okay, how it is done, even if it is, if it's difficult to now utilize these tools in some creative way. In if you go into any applications of cryptography, the hope is that you will basically detect, you know, you will be able to smell a rat. So like, if there's something wrong, then maybe this will ring a bell. Like, wait, what are they doing? Like, is it supposed to be like this? What is the, you know, are they using these tools correctly? I remember that it was not such an easy thing to move between one and another, or to, you know, just assume that the elliptic curve pointer is a random string, or I don't know. These things matter, and they're very often wrong in applications. So it depends, like, you know, if it's a standard that is examined by many people, then even there are mistakes. Even there are implementation mistakes, like implementation details, which by the time it goes from cryptography to the system, it's basically wrong still, okay? Because somebody misunderstood something along the chain, or mess something up, like in a software update. But with systems that are developed by, like, you know, a company just like wants, okay, so we have a startup and it's a communication thing, and like let's put the security, let's authenticate the users and create keys, etc. And what do we do? Like, what tools do we use? So you should be careful. And any kind of, I've seen people create like all sorts of weird stuff, and it's like it will be luck if it's okay, because most of the time something is messed up. So what do? You have standards, but which standards? You have to understand which standards, what is the things that the standards give you, and hopefully you do. Okay. So a state of sort of mental paralysis that might happen when I'm giving you all these like pictures and so forth, right? Like we're like, okay, maybe that's true, but what do I do with it? Hopefully will translate that at some point down the line, you will use it to critically evaluate what's good, the bad stuff from the good stuff, and contribute to making, communication infrastructure more secure in this way. Okay, a little prep talk. Or at least that's what I'm hoping for. You can, because I think that I'm not sure if we have like one more week or two. We might have only 1.5, or actually 1, right? If there is something that you particularly want to learn about, send me an email or post it on Piazza, because there's lots of stuff we could do. Learn about RSA, learn about elliptic curves, learn about signatures, all sort of stuff. And put on Piazza if there's something that you're feeling like, can we possibly cover? Okay. So I'll see you.